week of the year. And yeah, so I'm going to do a couple of intro slides and then we'll just get started with the lessons for the day. So first of all, I just want to open with why this workshop exists. Most astronomers, including a lot of us and including the TAs and instructors, don't have any formal education in programming. So from a purely astronomy perspective, this causes bugs in code, poorly documented or hard to read code, inefficient code that isn't reproducible. I'm sure a lot of you have had experiences where your advisor gives you a piece of code that is terrible and poorly documented and you spend hours and hours trying to figure out how to use it. But also from a personal perspective, it makes us feel bad. And every year when we read the applications for this workshop, we see everyone saying I'm embarrassed about my code. I feel like I'm not a good astronomer because I can't code well. I really want to learn to be a better coder so that I can, feel better and be a better researcher. So luckily, it's actually not that hard of a problem to fix. You really don't need to have majored in computer science to learn how to write good code. So the purpose of this workshop is to help you develop the habits of excellent software developers. So you'll see this slide several times during the week. These are the three main goals of the workshop. The first goal is that by the end of the workshop, you're going to be able to use the language of software development. You're going to be able to develop and release an open source astronomy package from start to finish. And that's the point of the project, is for you to, from start to finish, develop your own software package and release it publicly. And third, write code that follows best practices of software development. So I want to point out there's a cheat sheet for this workshop that we made, I think, in the second or third year, just because there were so many different links to things flying around. So I'll show you what this looks like. So you can find this by either just going to these intro slides and clicking on this link, or you can just Google code Astro. The GitHub repository will be probably one of the first things that comes up. And then you can just look for workshop info. So this is the landing page of the GitHub, and then you just go to workshopinfo.md. So we've got all these different links. I'm going to go through what all of these are in the rest of these slides, but this is sort of a cheat sheet. If you ever find yourself wanting a link, you can come back to this. All right, so now we're going to take a couple of minutes to just briefly introduce ourselves. So yeah, my name's Sarah. I use she, her pronouns, and I'm a postdoc at Northwestern. I'm starting a new postdoc at UC Santa Cruz in the fall. And yeah, I've been teaching for Code Astro for 5 years. I was a first-year grad student when this started, which is crazy. Jason, you want to go?
Yes. Hi, everyone.
Oh, wait, sorry. All the in-person TAs, you want to come up so we can transition quickly?
Come over here. Hi, everyone. My name is Jason Wong. I use he, him pronouns. I'm a assistant professor here at Northwestern now. Yeah, it's been a blast having Code Astro, and good to see everyone and everyone's smiling faces.
Matt.
Great. Hi, everyone. My name is Matt Hosick. I use he, him pronouns. I'm a postdoc from UCLA. I've also, I think, been here 5 years with these guys. I overlapped. Club. Yeah, I've overlapped with Jason in grad school, so that's how we got connected. But it's been great. It's an awesome community, and excited for another year. So thanks for being here.
Thanks. All right, let's see. Maria. Oh.
Hi, my name is Maria.
Sorry.
Sorry about that.
Why don't you make sure you can? No,
it's okay.
Don't worry about it.
Okay.
You can look in the video.
Oh, that's right. Yeah, sorry. Okay, hi, I'm Maria. I am normally not this chaotic. I use she, her pronouns. I am a rising fourth-year PhD student at the Institute for Astronomy in Hawaii. And I'm currently based at the Keck Observatory because of my thesis. And that's my contact if you have any questions. My thesis is sort of 2 parts, and both parts have significant amount of coding. The first part is high contrast imaging of disks, which is a very, very fancy way of saying, look at a young star, look for things of dust and gas around it, and take really nice, crispy pictures. And the other part of my thesis, sort of related to it, it's adaptive optics instrumentation, which basically involves working with this workflow that has a, to quote my favorite character, a wibbly wobbly timey-wimey mirror. So yeah, I do a bunch of optical alignment, optical design, which I'm trying to work on, and characterizing and testing a new deformed mirror. I helped with one that was recently installed in Subaru, and my thesis is about working on one that will be installed in Keck next year, this time. So my main programming language has been Python. I've also used Unix and MATLAB, so if you have any questions, I should be able to help, maybe. And I primarily use Mac and Linux. I have used Windows when my Mac broke down, so some experience with that. I was a Code Astro student back in 22, which was the end of my first year of grad school, and I learned a lot. It is a very, very useful experience. It helped me understand how GitHub architecture works, helps me understand how to work with a team on a coding project, which is very helpful because right now I'm working with a team at Keck to basically revamp the whole software architecture from taking everything from IDL to and making it Python compatible and kind of making our whole system from controlling a little piece on a DM to controlling the entire AO system with a very uniform, easy to understand Python architecture. So my experience with Code Astro is super useful now because I know how to talk to other coders, I know how to work with a team, I know how to code better, make my code readable and things like that. And when I'm not working, I do a lot of public and education outreach, things like talking to kids at an event about astronomy and making them sort of think about what's out there and telling them that there's a cult of astronomers that you need to join. I do a bunch of SciComm. If you've heard of Astrobytes, it's a journal. It's basically a nice, cute magazine which reports papers and a lot of other things, mainly for undergrads and early grad students to keep up with latest astronomy research. There are a lot of Astrobyte authors here actually, so if you have any questions about that, would like to join our club at some point, you should come and talk to us. And when I'm not working, I love hiking, snorkeling, scuba diving. I live in Hawaii, so it's a given. I do a bunch of blogging. I love reading, and if you are into mysteries and thrillers and historicals, TV and movies, come talk to me. Yeah, thank you.
Yay, thanks. All right, Lisa, are you online?
I am, yes.
Oh, I didn't set up the. Sorry, this is my bad. We didn't set up the sound correctly. Give us 1 second.
Oh no, I pressed the wrong button.
Oh no.
Out of all the buttons I pressed the power button. To be fair, it's right next to the sound up button.
I'm sorry, Lisa. Why don't we, in the meantime, have another in-person person go?
Yeah.
Sushi.
Projector's booting up here.
You go a little faster too. Yeah. Thanks. I don't know how it works. Oh, I'm sorry.
There you go.
Okay.
So hi everyone, I'll just be a little bit quick, but if you see anything that you want to come talk to me about after. I'm a 5th year grad student. I work on astrochemistry, both in the laboratory, through observations and through modeling. So if you're interested in anything chemistry-wise, I'm happy to talk about like interdisciplinary science. And one thing that I did want to highlight is that something that I've been involved in throughout my entire grad school career has been climate advocacy work through Astrobytes and through AAS. So if you're interested in that, there are a lot of resources that I put in here, but you guys can see this in your intro slides. So happy to chat more about anything after offline.
Hey, thanks, Gucci. Okay, Lisa, you want to try again?
Okay, is it working?
No. Sorry. Is it just the volume?
It's this. We're gonna make sure we get the right speakers.
Okay.
Can you try again?
Testing.
Okay, now we hear you.
Okay. Hi, my name is Lisa. My pronouns are they, them. I'm a 5th year PhD candidate at RIT in Western New York. I study moderate redshift galaxies. I'm using SED fitting. I mainly program in Python, but I like other languages too. I'm using Mac, but I'm familiar with Linux, and I'm excited to be here this week. Thank you all.
Awesome, thank you. We broke up a little bit for the in-person folks, but we will get to know you over the course of the week. Siddharth, are you? No, Siddharth is still traveling, right?
Yeah.
Okay. This is Siddharth. Everybody say hi.
We have some flight delays.
Yeah.
Yes.
And Pranav also is having travel issues, correct?
Yes.
This is Pranav. Everyone say hi. Okay, Marcel.
Hi everyone, my name is Marcin and I am postdoc at Xiamen University in China. I was born in Poland, if that makes any detail. And currently I am working regarding the reverberation mapping and my PhD was done doing the SED modeling with the accretion disk model, Novikov-Tornshek or Sunayev. So if you have any project regarding that, I'm happy to help, or the measurements of the disk sizes. I was participant, I think the first hybrid one, 2021. So this was a COVID time, and I am happy to be here as in person as ITA. So glad to meet you all.
I'll let you guys look at that.
Amazing.
Wow. Don't worry, it's not long. It's 10 seconds.
That's sick.
It should be that now, sorry. Yeah, so I started as an engineer and
Look into
decided I was being too productive, not good for the economy, and so I switched here. And I've been doing Astro since like 6-7 years now. But most of my, I say I do Astro, but what I do is coding, just coding. Like every time I am on my laptop debugging something, that's it. And I currently work on Hammer and Hammer with Dr. Matthew Liska. It's a very scalable GPU accelerated code, and he has a title for like running the most robust simulation, GRMST simulation that has AMR. AMR is adaptive mesh refinement for the longest time on the biggest supercomputer. And I'm trying to steal that crown. So let's see how many years it takes. And I was a participant in this 2022 Code Astro, and it was a complete mistake because I clicked the wrong link on Facebook. But now here I am.
That was a fortuitous mistake. I didn't know that. Sam, are you online?
Yeah, I'm here. Can you hear me? Hello, everyone. I'm Same. I'm here to help you with Discord. I'm a last year PhD student at Cologne University in Germany. I'm from Palestine, and I'm studying active matter, which is basically when you look at one thing that's moving randomly and it looks boring, but as a group it's interesting, like fish or bears. This is what I'm studying. We are trying to understand them and simulate them. And I've been before ITA twice for Code Astro. I've been at the first one as a participant, and now this is my third time. For OS, I'm daily using Windows at home. In the office, I'm using Mac for the analysis and Linux for the simulation. For programming, basically, I'm using Python and an open source package called LAMP, which is basically based on C++, which can be used for many things. So if you want to know something about it, I can help you with that. I'm here. See you.
Awesome. Thanks. Vivek. All right, Kruti, you online?
Yeah. Hi, everyone. My name is Kriti. My pronouns are she, her, and I broadly work on gravitational waves and their multi-messenger follow-up. Ever since Code Astro, I've been really keen on software development that sort of aligned with my bachelor's thesis too. So yeah, I participated in 2020 as a participant, and since then, this is my third year TAing. And a little bit about my trajectory. Essentially, I've deferred my PhD to focus on my hobbies, Kathak, I sing, Western vocals, and sketching, painting, and I try to read a bit. And also, right now, I'm catching a lot of live shows So yeah, if one of these days, if you see me in a very different outfit, very traditional outfit, or very fancy outfit, don't mind me. I'm just in between things. So yeah, I'm very happy to be here, get to know all of you. So yeah, excited.
Yay, thanks. Ray, is Ray online? I think Ray might be missing, but Ray is great, and she is also in charge of the Discord in addition to Sama. Shoot.
I don't see Shu.
Okay, this is Shu. Everybody say hi. Two quick more things I wanted to say. So the goals for today's activities, which we're going to get started with right now, are first to be able to identify which development environment is most appropriate for your programming task, decide when and how to use design software, how to design software using functional and object-oriented paradigms, use Git to contribute version-controlled code, define Git flow, and give examples of the advantages of Git flow. The project goal for today is to decide on the purpose of the package and to write a central function or class and put it on GitHub. So as an example, I'm going to use this example throughout the week. So me and my partner are working on a project that plots the most likely galactic orbits for a user-specified subset of the Gaia catalog. Today, me and my partner are going to write a function that uses GalPy to compute and plot orbits for a list of stars, and partners 2 and 3 will write a class for constructing the list of stars using user input. We're going to use 2 separate Git branches to do that. Okay, and then before we get started, actually we're going to do this, you don't need to do this right now, we're going to talk a little bit about how to do this during the Git lesson, but we're going to remind you to do this every day. So since we're making changes to the GitHub repository with Code Astro throughout the week, we want to make sure you always have the most up-to-date version. So you can do this by typing this series of commands, like cding into where you're storing Code Astro. This command, git stash, is going to stash your personal changes that you've made. So you can pull in everything without worrying about conflicts with your changes that you've made. Then pull in the changes from GitHub, and then this will reapply your changes. You can also do this in VS Code directly. So I'll show you how to do that if I can exit. 1 sec. Oh, I'm on Code Astro. All right, so if you have your Code Astro open on VS Code, you can just click this little button here to sync everything. And so it should, if there's no like little arrow that says it's pointing down, that means you're all synced up. So that's exactly the same as that complicated list of commands that I just put on the last slide. All right.
Let's get back started. Okay, let's get back started, everyone. So for our first lesson, we're going to cover for the next hour. We're going to cover both software development environments briefly, and then we'll talk about kind of how to design code using either object-oriented or functional programming. So first, we're going to talk a little bit about software development environments. This is where you're actually writing your code. So there's kind of there are many different options. We're going to really try to teach you one of them. The main one we're going to try to teach you is what's called integrated development environments, or IDEs. Integrated development environments, these are all-in-one kind of programs that come with many different features that let you help you code. They're more than just like you being able to write text to a file. They have a lot of features and buttons, and sometimes it gets confusing how to use them more than just writing code. But we think it's worth the small amount of effort to put in to try to navigate through all those features because it will help you write code in the long run. It will save you time. So the 2 of the leading what's called IDEs for Python are VS Code and PyCharm, and we're going to show you how to use VS Code throughout the week. The same kind of features and principles apply to both. So if you use one, if you learn VS Code and then start using PyCharm, you'll see that the same kind of features exist in both programs. They'll just be in different places. So it usually takes like 5 minutes for me to find the right button the first time of where I need to click to get to the right feature, but they'll have all the same features. So I'll just give you a quick little tutorial on VS Code, although also check out the video from the Day Zero installation guide that Sarah made that gives you a more detailed introduction on VS Code. So this is VS Code. There's kind of three main components to, I'm going to take this. There are kind of three main components to the program. One on the left, this is your file browser, so you can see all of the files that you have. You open up a specific folder. I've opened up the entire Code Astro GitHub repo here, and I can see all these folders and subfolders and all the files within the folders. The second thing is this is where you can actually view your various files. So if you click on a file here, it will open it up. So this is where you actually are doing your text editing. So that's like your normal text editor, just like any other text editor. And then on the bottom, this is your terminal. So here I can actually run commands like I would with any other like any terminal I open. So it puts everything all in one place. So that's why it's called integrated development environment. It integrates everything. You could do things in here, like you can make a new Python file. So if I go in here and do something like test UI, I can create a new Python file, and I can just start coding in it like I do with any other coding environment. So let me zoom in, make this it's too much. Make this a little bit easier to see. I'm going to close the terminal so we can get distracted. So I can do import numpy as np. So you can see as I'm typing, we get this nice syntax highlighting that appears. And the other thing is if I do something like call a numpy function, it automatically starts suggesting me all the possible numpy functions I could possibly use. So this is called autocomplete, and it's very useful in case you're like, I forget exactly what this function is called, but I know how it roughly begins. You can just basically give you a suggestion for what function you're actually trying to call. And then once I hit this parentheses, it will actually give me the entire documentation for the function as it appears on the NumPy website, but just as a little blurb. So I can scroll through this blurb. It'll tell me like these are the arguments that you can put into here. You can go all the way down to the bottom. Here's the examples for the NumPy. Like how do we actually have to call the function? So you can copy one of the examples. And then once you leave that, the autocomplete, the little tooltip disappears. So it has all these nice little hints and features to kind of help you code. And then if you try to do something like sum equals to numpy.sum of r, but you actually like mistype it and call it art. You can see that the little spell check thing, just like on word processors, appear underneath it, and it tells you that this is a variable that's undefined. You have like you never defined this variable before. There's probably something wrong here. So it will point that out for you so that you don't have to wait until when you're running the code to run into these errors. While you're programming, you'll automatically find all of these errors for you. And then you can go back there and be like, I should go fix that. And once you fix that, that little squiggle disappears. So those are some of the nice features of VS Code that we think will help you with things. The other thing that is nice that you'll learn a lot more about tomorrow. I'm just gonna give you a taste of it. Is the debugger. So here we can, on the left, there's a bunch of little different modes. We can go into this run debug mode, and again, we'll have a whole lesson dedicated to this tomorrow. But we can go into debug mode, and we can basically step through a function line by line. And basically, it'll execute each line of the function, and it'll go to the next line, and we can inspect variables after we run each line of code. And this is a very interactive and easy way to kind of figure out what's going on in your code without having to put print statements everywhere, right? You can literally do any sort of print statements you want for you automatically. So this is something we'll go into a lot more tomorrow, and you'll have more practice on, but I just wanted to show you these are some of the nice features. There's also GitHub integration. So you can also go into here. I won't explain it right now, but you can also go in there and do various GitHub related things that you'll learn about today and tomorrow inside of VS Code as well. So those are just some of the features of VS Code. There are a lot of various features. Many of them you probably will never use, but those are some of the main ones that we think are quite beneficial to anyone doing programming in astronomy, especially in Python. Okay. Yeah, and then yeah, the Git integration, Sarah also in her video also shows you how to use that. So that's why we're not going to demo it here right now. Other useful features that we didn't discuss about in the demo, VS Code has SSH integration. You can actually, any computer you can SSH into, you can launch VS Code into, and you can basically program on your laptop and open up files on a remote computer you access over SSH, and it will save those things there. So you get the nice VS Code development environment, not just a little terminal, and you can do all your programming in VS Code. All that code runs. If you do the debug mode in VS Code, that code will run in debug mode on your server, on the SSH computer you SSH into, but it will, you can control it all from your laptop in VS Code. So it's a nice way if you needed to access a remote computer and edit files. The Windows folks will learn about WSL integration, and there's this extensions marketplace that you can customize VS Code with many different additional plugins, and it can also be used to run a Jupyter notebook. So if you like to use Jupyter notebooks, you can also use them, open them up in VS Code. Although I actually prefer to open up in Colab or a web browser, so that's why you see me have it here. Okay, so those are IDEs. If you haven't learned about them, we'll try to make you practice them this week so that you can learn a little bit about them and see if you like them. The second thing are Jupyter notebooks like this one. Many of you probably are familiar with Jupyter notebooks. Jupyter notebooks are a combination of coding cells and markdown cells. It makes it useful for writing out tutorials. It's also very nice for kind of playing around with code because you can run and rerun cells multiple times. So as you kind of, you run something, it doesn't look quite right, you can edit that one cell. You don't have to rerun the whole software just to make one small edit. It's also very useful for plotting, solving problems. You can think of it as a document. As you're writing out how you solve it, it kind of gives you a living document for how you solved a particular problem in your research. There are some caveats with Jupyter notebooks. Because you can kind of rerun cells, whichever ones you want in any way you want. The output of your code in your Jupyter notebooks can depend on the order cells are run or rerun. So if you're like, okay, I run cell 1 and then I run cell 2 and then go to run cell 4 and I run it like 3 times, then I can go back and run cell 3 and then everything works. You're like, great. But like if you then 2 years later you try to rerun that same code, you're like, nothing works anymore. It's because you don't remember the order of which you need to run all the cells. So that's one of the caveats with Jupyter notebooks. And in particular, it's also really only designed as kind of to kind of work on it as a document, right? It's not really designed to work on an entire software package, especially if you have multiple files all talking with one another. You don't really want to use Jupyter notebooks or something like that. And then there are plain text editors. They're kind of your old school editors like Vim and Emacs. You might have heard of them. I don't know how popular they are nowadays, but people still use them. Even things, maybe some of the more, there are also fancier versions of them nowadays, but these are just general text editors that don't let you, all you can do is type. You type and you can save things. That's all they offer. We generally recommend against trying to do large amounts of programming on these because you don't get all these assisted features that you get with something like an IDE like VS Code, and that often then allows you to be more prone to bugs, especially for people that have written in IDEs for the last several years. Trying to go back to a plain text editor, my code is just filled with bugs everywhere because I forget how to write code without all the assistance basically that they give me. Sometimes inevitably you end up using it in astronomy, so it's probably good to learn one or the other a little bit. But nowadays I almost never use any of these basically. So like I almost use VS Code for almost everything. But I'm also like totally like drinking the VS Code Kool-Aid. So so this might be me. And like so like if I needed to SSH and go into a terminal and like edit code and on a remote server, I would just open it up in VS Code and edit it in my VS Code session. Cool. So that's everything on just kind of brief overview on development environments. We'll talk to you a lot more about VS Code over the week, but you probably are more familiar with the other two, so that's why we're trying to get you more familiar with IDEs and actually take the time to figure out where all those buttons are and how to get things set up, because the first time is kind of annoying and you're like, why am I spending 30 minutes doing this configure when I could just do this other thing in 5 seconds? Hopefully in the long run, it'll be useful. Okay, so now let's talk about programming paradigms. In particular, we're talking about object-oriented versus functional programming. So those are two of the more popular paradigms for which software is developed, like how software is structured, how the API is laid out, and what are kind of under overarching principles behind those designs. So we'll talk a little bit about object-oriented programming. We'll talk a little bit about functional programming. And I just want to remind everyone, the last TLDR is that these aren't absolutes, right? You're not in one camp or the other always. Like oftentimes many programs, especially many open source software packages, have a mix of those paradigms. So it's not like, oh, everything needs to be object oriented or everything needs to be functional. You actually end up seeing many programs have a little balance of both depending on what the specific use cases of various aspects of a package are. Okay, so let's first talk about object-oriented programming. So let's take a second to appreciate the meme. This workshop is 5 years old, so some of the memes are a little dated. We're working on updating the memes, I promise. Okay, so why is object-oriented programming right now very popular in astronomy? So object-oriented programming is popular because of this. It's really based around this idea of using classes to kind of model things. So classes, what are classes? Classes are kind of constructs in programming that organize variables and functions all into a single object. Like for example, is we can create a telescope class. Say we're trying to control a telescope. The telescope class can have functions like telescope.close shutter. So that closes the shutter of the telescope. It can also have attributes like telescope.current target. What is the current target we're looking at? So it can have a mix of various functions and attributes that all belong to that class. Objects are useful because they can track the changing state of the world, and lots of things in the world that we want to model kind of have some inherent properties that change over time. And it's useful to kind of put all those things inside this construct, so it's all very nice and organized. For example, telescope that current target, that attribute will change anytime our telescope slews to a new target. And it's useful to have that as a possible thing that we can access, when we want to know what are we currently pointed at. Classes can also have this more advanced kind of feature of what's called inheritance. And this is what a class can actually take the fields and functions of what's called a superclass or a parent class. This is useful for reorganizing or reusing code. So for example, in our telescope example, we can have a subclass called space telescope. This subclass space telescope will be a subclass of its parent telescope class. And that means that it inherits all the attributes and functions of its parent class, like closed shutter and current target, because those are things that are applicable to space telescopes as well, for the most part. Whereas a space telescope may have other things, other attributes like distance to Earth that are unique to a space telescope that are not things that all telescopes care about. So the attribute distance to Earth is an attribute of the space telescope class, which is a subclass of the telescope class, but the telescope class itself does not have the attribute distance to Earth because it doesn't need to know. Not all telescopes need to know the distance to Earth. So this is a way we can try to organize things that, we don't have to rewrite the code close shutter or current target multiple times. All telescopes, space telescopes or otherwise have those. But space telescopes can have also their own unique things that are separate. Yeah, one second. And then if you have never seen classes or superclasses before, I encourage you to check out the diagnostic notebook for the basic syntax of those things. Okay, you have a question?
Yeah, very quick one. I was just curious about the inheritance aspect of it. Say, for example, you do class telescope, have a function closed shutter.
Mm-hmm.
You want to also use that for space telescope,
Mm-hmm.
but you want to use the closed shutter function
Mm-hmm.
that's inherited. However, there's a slight tweak that you have to make
Mm-hmm.
that's specific to the space telescope.
Mm-hmm.
Is there a way that can be modified,
Mm-hmm.
but still use from the main function closed shutter?
There is. So there's two ways. So what? Oh yes. So the question was, if we had a space telescope class that also wanted to implement closed shutter, but we wanted to implement it in a slightly different way than the original closed shutter implementation in telescope class, how can we do that? there's two ways. One is to completely just overwrite this definition of closed shutter. So you can totally do that within your class. You can a subclass can rewrite its own implementation that supersedes the existing parent implementation of something. You can also do a combination of two where you partially overwrite it, but you also partially call the code. And in particular, you'll see this kind of second way of doing this when we talk about our activity that you're gonna work on. This is a way you can basically both call your the parent version of the implementation and also do your own thing at the same time. Okay, so this is all kind of really high level, and I feel like the only way we're gonna be able to learn this in the next 30, 40 minutes is to actually just do it. So you guys are gonna build a little mini gravity simulator. So the goal of this is to build a free fall gravity simulator. So, and use your simulation to determine how long it takes for a particle to fall from the ground at rest from a height of 10 meters. So, you can compute this. This is like, in your undergrad physics class, you can figure out what the analytical solution is. But we want you to do it through coding and through a little simulator tool. So how is this going to work? We've already put a lot of the structure in there for you. So first, we have this particle superclass. You don't have to worry anything about it for now. This is part of a bonus activity to think about how to actually design this particle superclass. But what you'll be focused on is defining this, working on this free fall particle class. So this free fall particle class is a subclass of the particle superclass. Currently, the particle superclass does nothing. So it's a subclass, but it doesn't really matter. And the goal of this free fall particle is to simulate a particle falling due to Earth's gravity. Particle is stationary at first. And then we'll also have some example code that we can start out with, and you can see that we can initialize the free fall particle with this initialization free fall particle parentheses 10. And that tells us that we want to start our particle to fall from a height of 10 meters above the ground. And what happens there is that when we call free fall particle parentheses 10, it calls the init functions. And init function is a special function of all classes. It specifies how an object of a class is created, how an instance is a technical term of a class is created. And it's always spelled out underscore init underscore. That's how it's done in Python. And the first argument is always self. Self refers to the particle itself. It refers to this instance of the object. And then you can have other required arguments or optional keywords as well. Here we have a required argument height, which is the height that we start out the object from. And then a dt is the time step of the simulation. For every step in the simulation, how much forward do we want to advance the simulation in time? And here we're specifying 0.1 seconds. So when you call free fall particle parentheses 10, what happens is that the following code is run. So you can see this is where I mentioned you can do a hybrid version where you can call the superclass implementation, but also do your own thing. Here, basically for all initialization, it's always best practice to start off with by calling your superclass initialization. So you call super parentheses dot underscore init underscore, and this will call the init class of the particle superclass. Right now, the particle superclass has nothing, so this call does nothing. But if this call had stuff, those lines of code will be run when you run the superclass init. So this just lets us basically instantialize all the attributes of the parent class. You generally always want to do that first. And then after you've instantialized all the attributes and various things of the parent class, then you can add additional instantialize various other additional attributes of your class. So here we've set up the height attribute. This is the current height of the object. We have the velocity attribute. This is the current velocity of the object in meters per second. The current time of our simulation, how much time has elapsed in our simulation. We start at 0, obviously, because we haven't done anything yet. The self.dt is the time step of the simulation. So this is what's defined from our optional argument that gets passed in. And then self.g, which is the gravitational acceleration, which is negative 9.8 meters per second squared. So this is how the state of the simulation starts out. We start out with a particle at a height equal to the height we pass in, starts out at rest. We haven't started our simulation, but we know the time step of our simulation and we know the force of gravity. So that sets up the stage for setting this ball to drop down from the ground to the ground from a height of 10 meters. This function can have other various helper functions. You don't have to use any of these. Just kind of give you a sense for like how classes are structured. We can have a function called like get num steps run. This is a function that returns a number of timestamps that have elapsed in our simulation so far. And we basically just take the self.time divided by self.dt, and we get the number of steps, and we return it. So you can see here, the only attribute here, the only thing that gets passed in is self. And self is useful because we can then refer to these attributes of ourselves. We don't have this variable as the first. So all functions of a class should have self as the first function, a first argument that gets passed in, so that you can always refer to your own attributes. So you always want this as your first argument of a class. Okay, so your activity is to actually implement the free fall simulation. And we're going to do this using the simulate time step function. So you want to basically add the ability to, for every, since your simulation's at a given time step t, and you want to be able to advance it to a time step t plus delta t. So you want to be able to advance the particle's height, velocity at a new time step to the next time step. So you know the acceleration is g. We can compute the new velocity by computing the current velocity and adding the acceleration over the next time step delta t. And we can compute the new height by taking the current height and adding the new velocity times the current time step delta t. So this is some pseudocode for you to use. And you want to be able to, so your goal is just to modify this code here to basically advance your simulation to move forward by one time step at a time. And then you'll have, basically you want to be able to call this ball.simulate time step function multiple times, enough times until your ball hits the ground. And then you want to figure out at what time t in our simulation, how long has it taken for the ball to hit the ground. So currently, if I run this, because simulate time step is not implemented at all, the ball kind of just stays. Time always stays at 0 seconds, and the height always stays at 10 meters. And that's not optimal because we want the ball to fall to the ground with gravity. So your goal is just to implement this. If you have time, try to think about how you would design this code if we want to, in the future, want our particles to experience other forces and move in 3 dimensions. So we want to be able to implement this particle superclass that is able to kind of handle simulations in 3 dimensions, and think about what fields of our, what fields should go into the particle superclass and which fields should remain in the free fall particle subclass. So that's kind of the bonus activity if you have time. At the end, we're going to create a Piazza post and reply to the Piazza post with how long it took based on your simulation for the ball to fall to the ground from a height of 10 meters. So there'll be a post on Piazza. So anyone on Zoom or in person, you can all reply to the same Piazza post. Again, we'll try to do the pair programming paradigm. So pick one of you as to be the driver. The driver should just be in charge of asking navigators, like, what should I be writing? Tell me what I should write. And the navigators, you are in charge of the one time you are allowed to do backseat programming to look over someone's shoulder and suggest to them what's the next thing that they should be writing. So we have some instructions here. So let's give it a shot. I think let's try to aim for 20 minutes. 20 minutes, and so we'll come back at 40 minutes after the hour and recap. All right, so folks who are curious, here's my solution to the problem. So in my solution, everything is the same. The only thing I changed right down here in the simulated time step function, you can see I updated the velocity to it says to increase, but g is negative, so it increases a negative number, so it decreases by some amount based on gravitational acceleration and the time step of the simulation. And then the height also decreases, even though it says increased velocity is also negative. So this height will also then decrease, and then the time step will also increase because we've advanced our time step by 1. So the velocity has gone a little bit more negative due to acceleration. The height has dropped a little bit due to the velocity, and the time step has moved forward by a tiny little step. And then we can still return the height if we wanted to. And then here in the little code snippet below, you can see I've initialized the height free fall particle with a height of 10 meters. And I saw you guys were all being so very precise. So I also decided to add this in the last minute to give myself a few more significant figures. And we can print out the ball's initial time 0 and height 10. And while the ball's height is greater than 0, we keep calling simulated time step to keep advancing the time step forward by another time step until the ball's height eventually reaches a value less than or equal to 0. And you can see that happens at 1.42899999999. So there, I went in the significant figures game. No. Okay, so nice work for everyone that to do this. Like I said, if you didn't have time to finish it, you'll have time. You can look over this in the afternoon and finish it out in the afternoon. One thing before we keep going, I just want to mention for all of our activities in class, they all if you go to the Code Astro repo if you go to the folder for each day, so I'm in the day 1 folder, there's a README for each day. And in the README for each day, there are useful links to all of the notebooks. And in particular, there are collab versions. So if you are having issues running a specific notebook on your computer, you can always click on this link and it'll open a Google Collaboratory version. You can run it online, and it should all work online on Colab if you are having issues with your setup or anything like that, or you just want to run things on Colab. You can do it all from here. For each day, we have links to every one of our notebooks down here. So if you're ever confused where to find things and we forgot to tell you, like I just did before this activity, they are right over here. Okay, let's just wrap up on programming paradigms. So we talked a lot about object-oriented programming, and you got to experience it a little bit. What we kind of feel is that object-oriented programming is structured around the code. The code is structured around objects, and it really depends on the changing or mutable state of each object. So we just worked on this falling free fall ball example, or which are changing things like the height and the velocity of the ball. So our code is really centralized around these variables that are changing, and we're programming in a way that we are using the fact that these are changing over time to solve a problem. Many things in the world change, so it makes sense to frame things this way. So that's why object-oriented programming is generally popular. So when you're thinking about how to do things in an object-oriented way, we recommend before you start programming, identifying what are the entities that should become objects and program around them. For example, if you're doing a simulation, the particles in the simulation can be grouped together in a class. If you're writing like a data reduction pipeline or something that looks at data, or a data visualizer, like spectrum files all produced by the same pipeline probably all have the same format. So they can all be grouped together in a class and structure things that way. There are some subtle kind of things to consider when using classes. Not like classes is the solution for everything. Creating an object is slow. It takes memory allocation. So if you are making an object every time you do every individual step, you're going to eventually slow down your code to a point that you'll start noticing it. So you don't want to create objects for everything. It's a lot of overhead in doing so, both there's a runtime and also programming. Object-oriented programming also has a subtle thing, is actually more prone to bugs because the output of any function like simulated time step depends on both the inputs to the function, but also the current state of the object, which is implicit. So when you're calling something like simulated time step, which has no arguments, the return value, you have to kind of mentally visualize in your head, all right, it also has all these other this free fall particle object also has these other attributes like height and velocity, and those are the ones that are coming into play that causes my simulated timestamp function to behave in a certain way. So it has like 2 different ways that you can input things to cause the output to change, both the arguments that you pass into the function, but also the inherent state of the objects. And that second implicit thing can often cause bugs in programming. And then if you're interested in learning more, we offer a couple links on more conceptual discussion on object-oriented programming and a more technical guide on like how to use the various features of classes for object-oriented programming in Python. Okay, and then we're running a little late, but we're gonna cover briefly on functional programming. So let's take a second to appreciate the outdated meme. This meme is gotten even more outdated because functional programming is happening. again. Astronomy programming, usually software development, usually lacks the industry by, I'd say, around 10 years in terms of its programming paradigms. About 10 years ago, the industry started pivoting more towards functional programming, and you'll see in the last couple of years, astronomy has done so as well. And in fact, we even have an optional lecture later this week on JAX, which is almost a purely functional language. So this is actually coming back, and there's reasons for why functional programming is going to happen. So the key paradigm of functional programming is that your function outputs solely depend on their inputs. And this is easier to make testing. Remember I said for object-oriented programming, your function outputs depend on both your inputs and also the implicit state of your objects that can change over time. Here for functional programming, we always design our code so that our function outputs solely depend on the inputs. This is much easier to guarantee correctness. It has a caveat that if you have changing states of things, it creates more messier overhead for things to track, but you get the benefit of everything is always behaves the exact same way. There is a misconception that functional programming means that you don't use objects at all. That's not true. Many functional programming languages use objects all the time. So classes are often used in functional programming, but classes are often treated as what's called static data structures. Static means that they don't change. So every time you want to change an attribute of an object, you have to create a new instance of the class that has the new updated attribute. So that's generally how functional programming treats classes, that every time you create a class, classes are ways to organize things, but every time you want to change something, you have to create a new instance of the class that reflects the new changing state of something. That's why it makes it a little bit more messy to track the changing state of things, but makes it a lot easier to guarantee correctness of things. It's very useful things for like math problems, physics equations, unit conversions. Those are things that are very relevant to us. If you are familiar with AstroPy, and there is a whole optional lecture on AstroPy, AstroPy units class, the AstroPy units module is a perfect example of functional programming. So you have an object that's u.m, which is the meter class, but that class never changes. And you can always call u.m to u.nm and convert from meters to nanometers, and it'll always gives you 10 to the 9, right? It will never give you anything else. And this is why functional programming is useful for things like math problems where you always expect one answer given one input. There's another useful part of in astronomy is in data reduction pipelines where, and again, one input should always return a given output. And then just a couple things on comparisons between object-oriented and functional programming. Object-oriented programming is good when things change, such as the position of the planet, the current image being analyzed. Functional programming is good for much more deterministic things. And like I mentioned at the very beginning, most modern programming packages, software packages use both, whether they think about it or not. There's not one that's superior. So there's very few packages that are very extreme that only use one or the other, but most programming languages use a bit of combination of both. And in general, how you should think of it are these two different programming paradigms are tools, are engineering tools to solve a problem. Like each company or software group or collaboration will have different approaches to tackle a problem given these tools. And as long as the solution works for your team, then it's a good solution, right? There's no like, this is the right solution. It has to be object oriented. It has to be functional to be the right solution. These are just possible solutions to the problem and how you can think about it. And it depends on the problem you're facing. That's why we're teaching you these things as tools, but we're not saying, you should always be doing one or the other. Just recognize that you can be developing in these two kind of different paradigms. And at the very end, I'll just show you briefly how this freefall class will look like if it's written in purely functional programming. So here, our freefall particle class is much simpler. It is simply a particle with a attribute height and an attribute velocity. There's nothing else. All you do is we're storing the height and velocity in a nice little container called functional particle. And then we have this function called freefall time step. And if you give it a thing, it will simulate the free fall of the particle to the next time step. So the arguments are the thing and the time step, and it returns a new thing, which is the updated position and velocity of the particle. And basically, it takes the thing and it creates a new thing that's a new instance of the functional particle class with a new height and new velocity given the calculation. So this code that was in simulated time step is still here, but now you can see that now that this code is now returning a new particle every time we call it. And this has the very nice, so this is how we would implement it. I'm going to skip that. this has the very nice kind of, or depends whether you like it or not, guarantee that if you call free fall time step with the same object and the same inputs, output ball 1 and output ball 2 will be the exact same. They'll have the same outputs. So we run this, let's just run this. It's going to run a bunch of things, but we look at the very last thing it prints out. RD is the same. So it prints out output ball 1 height and output ball 2 height, and you see that both heights are the same. So given the same input, we always get the same output, which is not true for, remember simulate time step. Every time we call simulate time step, we get a new height because we are advancing the height of our simulation. So these are the two, this is like the dichotomy of how these different things, how we're structuring the program. Sometimes this is good, sometimes this is bad. So it's up to you to decide whether this is good or bad and whether you want to design things this way or not.
Okay, yeah, so for the next activity, we are going to talk about Git, which if you've never heard of it before, it's just a method of what we call version control or source control, which just means it's a way for us to track the change of the files, right? And I'll give you a moment to appreciate this never outdated meme about Git. So Git is extremely powerful, really useful, and used widely throughout astronomy and industry. And so that means it's really clear and easy to use, right? Well, there's a little bit of a learning curve, but don't worry about that because we're going to work a lot on Git during this workshop. Okay, so as I said, source control, version control, this is a way for us to track how files change. Now, why do you care? Well, there's many cases where we want to keep track of the codes that we're working on. For example, you write a code that's for a paper, it does an analysis. You want to save a version of that code. That way in the future, you could always go back and repeat the same analysis that you published, even if you make other changes to the code down the road. In a similar way, if you have a code, it's working great, and then you have a great new idea, and you change that code, and it breaks everything. Well, instead of having to manually undo all the changes you did, with version control, it's very easy to revert to the last working version of your code. In a similar vein, I think version control is really helpful for debugging. You break your code. There are lots of tools in version control that you can say what exactly changed between version 1 and version 2. There you go. You can do that a lot easier. And then finally, and what version control is used a lot for is with collaborative work, right? You and your partners, you're all working on one code base, one project, like we're doing this week. How do you edit the same code base without stepping on each other's toes and overwriting each other's changes, right? This is all what version control is great for. So our recommendation is to use source control anytime you're programming, all right? Even if it's just by yourself. And also you can use it for not just code, you can use it for storing versions of papers and all sorts of fun stuff. Okay, so we're going to jump right into our introductory demo. We're going to try a code-along demo, so well, it'll be a fun challenge. But okay, so in this demo, we are going to make a Git repository on GitHub and copy it to our local machine. It's called cloning. Talk about that more. We're going to talk about how to add and edit files to your Git repository. It's just the directory where all the codes are kept. And we're going to show you how to resolve conflicts between the remote version of your repository, which is going to be the one that lives on GitHub, and the local version, which is the one that lives locally on your machine. So we're going to try doing this type-long demo. However, if you get stuck, don't worry about it. Don't panic. Just try to follow along. At the end, we're going to have a 10-minute activity for folks to get in groups and try to work on any stuck points if they get lost in the activity. Okay, and further for the activity, exiting out of PowerPoint, it's taking a long time. Okay, great. Okay, so for this activity, there's a README file that you can follow along with it. If you go to the Code Astro repo, right, GitHub page, go ahead, click day 1. And then under day 1, there is a folder called Git Intro. And if you click that, there's this file that's gitdemo.md, markdown. The demo we're going to do is exactly in this README, so you can always refer to it later. And also, feel free to have that running along. Now, for this demo, you're going to want to have 2 windows open. One of them is going to be a web browser. As I said, you can have the README in one tab, but in another tab, you just want to have a GitHub, your GitHub open, right? You can go to your profile page, right? Just looks like this. And And when you're on your profile page, you can go ahead and click the repositories tab. And we're going to hold here just right now. So go ahead. So you have a web browser with your repositories here. And then the other thing you want to have open is your VS Code, which open here. And it is useful to have, for this demo, we're going to be using the terminal a lot. There's a couple different ways we can use Git, but we're going to use the terminal version for now. You can explore like the Git integration inside VS Control on your own a little later. But okay, so let's begin. So the first thing we're going to do is we're going to make a Git repository on your GitHub account. So go ahead to your GitHub page. And if you look, find a repository over here. There's a big button that says new. Go ahead and click that. And that gives you to a page that says, okay, we now want to create this new repository on GitHub. We can give the repo any name you want. They give suggestions, symmetrical memory. That seems like a lot to type. So I'm just going to write what I've done in the past and just do test Git. Description, we are practicing with Git. It doesn't matter too much what you put there. We do want to make this repository public for now. Again, it doesn't much matter. And let's go ahead and let's add a README file. This is just a nice default to have. That way, when we make the repository, there's something already in it. And then once you're there, you can scroll down to the bottom and click the button, create repository. And then there we go. The repository is made. So this repository is made on your GitHub account. We're going to refer to this now as the remote version of the repository, also as the origin. It's the thing up in the cloud, like the main version you can think of. Okay, well, this is all well and good, but we want to do work on our laptop to change this repository, right? So what we need to do is we need to copy this repository down to our local machine, which in Git vernacular is called git clone, right? And so the way we can do this, there's a button that says code here. You can go ahead and copy this HTTPS address. Just go ahead and copy. And now come over to your VS Code window in your terminal. And you can navigate to any directory you want on your machine where this Git repository is going to live. This happens to be in my code directory because that's just set up that way. But you for the purposes of this demo, it doesn't matter. You can put it anywhere on your machine. But what you do in the now in the terminal on the command line here, we use the command git clone, and then you can go ahead and paste that command in there. And you do that git clone address, and boom, now all of a sudden, if we do an ls, well, there's a lot of repositories there, but now we have a test git directory, and that has our README in it. So something useful whenever you're working with Git repositories, there's a really useful command that called git status, just like that. You click that, that'll give you, obviously from the name, the status of the repository. This will tell you, okay, we're on the main branch. Don't worry about that. Sarah's going to talk a little bit about branches later. But the main thing is your branch, what you have locally, it's up to date with the origin. Remember, it's the thing on GitHub. Okay. Great. Okay, so now if you're following on with along with the demo, we're going to move to step 5 now. We're going to add a file to our repo. So the way we're going to do that, let's add a file locally. So we can go ahead in VS Code. Let's open the new folder that we just made. So for me, it's code, Python. So I probably should have set this up a little faster. Test Git. Here we go. You can go ahead, open the repository. There we go. Sometimes the terminal window goes away. If that happens, you can just go terminal, new terminal, and then here we go. We're living again. Test Git. Okay, so let's go ahead and add a file using the new file feature. We're just going to click that plus, and we're going to name this file hello.txt. And if we do that, automatically it pops up in the third window in VS Code, our text editor. And let's just add a line of code. It doesn't matter. I'm just putting it as Git first. Okay. Right. So now if we go to our terminal window, right, if we do an ls in our directory, now this hello.txt exists. Well, now let's go ahead and let's rerun that git status command. And you can see that now the output from git status is different from what we had before. Git says, aha, I see there's an untracked file in here. You have this file hello.txt. But Git doesn't know whether or not it's supposed to keep track of this file. It doesn't know that, yeah, that you care that much about it. So the first thing we need to do is we need to tell Git, yes, let's add it to the repo. And conveniently, the command is git add, and then the name of the file, which is hello.txt. Go ahead. We enter that. It does its thing. If we were to run git status again, right? Once again, the return has changed now. It says, aha, yes, now I see that there's a new file. And then there's this line that says there are changes to be committed. And what that means is that, you know, this file is on your local machine and it's different from what exists up on the origin of the remote repo. Right? So there's change. Okay. So now at this point, we want to say, okay, this is great. We do want to go ahead and save this change to the remote repo. We want to commit it to the repo. That's the verbiage. So we use git commit, the name of the command. Then you do the name of the file, hello.txt. And then we have to add a little message string saying what we changed about this file. Git is always going to force you to do this. It's good coding practice anyway. It's good for debugging later on what happened. But so the way you add this little message, you do git commit file name, then -m, and then in quotes you can just put your message. So in this case, it was, you know, first commit made file. Okay, we do that. That's great. Then once that's done, we'll run our handy dandy git status command. And it's changed again. You see, I use git status all the time. It's so helpful. Now it says, aha, okay, we're still on the main branch. Great. But now our local version is ahead of origin main, the thing that GitHub, by one commit. That's the commit we just made. So then the final step here is we want to, I guess, publish this change up to the origin, which in Git verbiage is called git push. So this would be, the command is git push. We're pushing to the origin, pushing up there, and we're pushing to the main branch. Again, Sarah will talk more about branches in a little bit. Git push origin main. There we go. And then at this point, if we hop over to our GitHub repo, right, test git, let's go ahead and refresh the page. And just like that, we see that hello.txt there. Okay, awesome. So now let's go back to our VS Code, our local version, and let's change this file, right? Let's add another line that says second. You know, you can just type second and then Command S, that's the way to save it, at least for a Mac. Okay. Now in our terminal window, right, we can do our handy dandy git status, and it'll say, aha, I see that you have made a local change to hello.txt, but it has not been committed yet. You know, sometimes, right, well, we just changed it. It's pretty easy, but a useful command at this point that I like to use, let's say you change a file and you don't remember what changed compared to the repository, you can use a really useful command called git diff. Git diff, and then the name of the file that git status said changed. And then it gives a nice little printout. It says, you know, there's one version of this is just first. Now what you have locally is first and second. It just shows you the changes. That's just a nice little tool just to figure out what changed in case you lose track. Okay, so let's go ahead and let's commit our change just like before. So git commit hello.txt. Remember, we always have to add that message line. Second change. Do that, then that's good. And then finally, right after we commit, we'll go ahead and push that commit up to the master branch. So we have git commit, git push origin main. There we go. Okay, and if we look at once again, kind of we refresh your Git repo, and you can click on hello.txt here, and it says, aha, now we have all the changes that you made locally. They're now synced and pushed up to the remote. Okay. So that's going one way. What about the other way, right? We also want to know, like, because especially when you work in groups, right, your collaborator, your coworker may make a change to the code base. You want to bring their changes down to your local machines as well, Yes, question.
Just what's the difference between just git push and git push origin?
Can you repeat the question?
Yes. So the question is, what is the difference between just git push and git push origin main? Git push, I think just a generic git push. Okay, so you can have like multiple branches of a code on your machine all at once. I think git push pushes all the changes up. You can have like main branch, development branch, feature one branch. It would basically push all the changes that you've committed locally up all at once. And sometimes we don't want to do that. So by doing git push origin main, it's specifically saying, okay, I am only want to push the changes I've made to the main branch up to the origin.
I think it actually might be the git push is short for git push origin main. It'll like the default is, yeah. I'm not 100% sure, but I think that's
okay.
Anybody else know?
So I know certainly you can git push and like specify like git push only a certain branch or git push other. Okay.
I don't know. That's a good question.
I think you can also make, like, if you made a new branch, you can like push your changes to that new branch instead.
Yeah. Well, that's like you can specify like git push origin dev instead of origin main. But okay, the straight git push. Okay, you know what? I'll have to double check that and make sure I'm not saying anything wrong. Then I'll have to get back to you after that. But it's good to specify it all. Okay, great. Okay, now we're going to go the other way. Let's go ahead. Let's make a change to hello.txt. We have to manufacture this a little bit. Normally, your collaborator or coworker would be doing this, whatever. But in order to simulate it, let's open hello.txt on the repo. Right? Let's modify it manually. There's a button over here that says edit the file. This is not usually the way I'd recommend editing files on GitHub, but again, this is just for this demo. And let's just go ahead and make a change. Let's make our third change. Then you see there's a nice button here, commit changes. That's what we had did before. So we had our message, third change. Then we commit it. Okay, the important thing is that change is now up here. Okay, so how do we get this down locally? Well, the command is called git pull. And once again, we're going to specify git pull origin main. We want from the origin, we want to pull down that main branch. We do that. Right? Git does this thing, and now look, now locally, now we picked up that change. Okay, so final thing want to cover. So that's the basics going up, coming down. Inevitably, what you'll find when working with Git is you often run into conflicts where you have a change on the origin and a change on your local branch that are incompatible with one another. And so Git doesn't know what to do. So we have to resolve that conflict manually. So to simulate one of these conflicts, let's go ahead in VS Code, line 7. Let's just make a change locally. We'll call it fourth. That's not how you use fourth? Yeah, okay. Fourth local, right? We'll just have that change, and we'll go ahead and commit it, but don't push it yet. We're just going to do git commit hello.txt, and then right, just like before, then we put the message for local commit. Okay, so that's all set on our local side. And then once again, if we hop over to our web browser, now we're going to simulate a change up on the origin. We have this hello.txt here, right? We're going to edit the file. Do this directly. Let's also edit line 7, right? One space between there. And here, let's put the text fourth remote. Right? And then same thing, we can commit changes. So we put our message in, fourth remote, commit changes. Okay, so now we're ready to set up our conflict. So how does this work? Well, okay, if we're in our local machine, right, we had just committed our fourth local change. Usually with our flow, we would say, well, let's go ahead and git push origin main. But now Git is going to say, you can't do this because it says, I see that there have been changes to the remote that you need to pull down. You need to bring down those changes first before you can push up your new ones. That's all. So we say, okay, well, fine. And you can do our command now, git pull origin main. run that. And this is where a conflict will come up. Now, if the changes on origin and on your local machine, if they don't conflict with one another, Git will just merge everything automatically. If your collaborator has edited a completely different file or different lines of the file, this will just work, and then you'll be fine. But in this case, right, if we look at our editor here, we see that we have changes to the same line, and Git throws up its hands, and now we have to help it out. Right, so Git will add new characters to this file. You see there's this like lesser than signs, head, greater than, a long change. This is basically saying, okay, well, I see here's the local change on the upper side, above the equal sign. Here's the remote change on the lower side of the equal signs. Git is going to say, okay, you as the user figure out how to blend these together and fix it for me. Right, and so we can do that just by editing this file directly. So we want to get rid of all like the equals and greater than, right? That just highlights the differences. If we wanted, we could delete one entirely. We could keep the other. In this case, let's just keep both of them. So I've deleted all that. I'm going to save the file again, right? Okay, now I've resolved this conflict. Yeah?
Simulating this on also my computer too, I don't get the same text that you were just showing earlier, and I'm wondering if you have an extension that's doing it, because I'm actually getting something different that says need to specify how to reconcile divergent branches.
That's a.
You saw the same thing.
Let's figure out the individual issues.
Yeah. I think we'll do that at the. Yeah. Let's circle back on those. Yeah, we're. Okay, so let's say you have this kind of conflict. You kind of have this set up. Okay. Now we have to resolve this conflict. What we have to do is we actually have to go back and git add hello.txt again. This kind of thing. And now when we do our git commit, what I found is that you can't do git commit file name. It's a little different. You just do a general git commit, then just -m fixing merge. So I'm not entirely sure why the syntax is that way. Open if folks know why, but just do a git commit -m fixing merge, then it does that. And then finally, after you do the commit, git push, or you can do your git push origin main again, and it resolves and everything updates. If we go to our repo, we refresh, and now the changes are up here. Okay, great. So I know we went through that a little quickly, but don't worry. As I said, we're going to go into a demo right now or an activity. Where's my? Oh yeah, I minimized it. Here we go. Okay, great. So now we're going to move on to our activity. So in this activity, let's go ahead and break up into your groups, and let's go over any problems that you had trying to reproduce the demo. Work together to see if you can resolve any of the issues as a group, and if you can't, feel free to ask one of the TAs or us as we walk around the room. And then if there's time, pick one group member, everyone clone a demo repository from that group member, and then try to edit the same file. You will get conflicts. See if you can resolve those conflicts on your own. Great. And so I will leave up here just kind of a quick little summary of Git commands. But other than that, go ahead, break out in your groups. And I guess in 40 minutes past the hour, we'll come back and then we'll be done. So okay. Thanks, everyone.
Okay, so I think what we're going to do is we're just going to go over the conceptual overview part today. And then tomorrow we're going to do a demo and then the activity about Git flow. So I won't keep you too much after. All right, so the goals of this lesson are to be able to describe the basic Git workflow, which we shorten to mean Git flow, create multiple branches within a Git repository, and make a pull request from one branch to another. So the first thing we're going to do is a really fun game that I'm so excited about. We're going to do a matching game. I bet you all were so excited. You woke up this morning, you're like, I'm going to kindergarten. I'm going to do a matching game. It's going to be so fun. Okay, so I'm going to give you 3 minutes. The point of this is to get us all on the same page in terms of vocabulary, because I'm going to use all these vocab words a lot. So I want you to take 3 minutes and just match all of these together, and then I'll go over what I did. All right, go. You can do this by yourself, by the way. All right, I'm gonna give you 30 more seconds. All right, time's up. I hope that was fun. Totally silent matching game. That was more awkward than I thought it would be. But yeah, let's go over. So Git, let me make sure I can point to it. Yeah, Git is a piece of software that defines, reads, and modifies repositories. GitHub is a website that stores repositories and interfaces with Git. So critically, the difference between Git and GitHub is that Git is a piece of software you can use on your computer. GitHub is like the website that stores things and uses Git. Source control is the practice of storing changes you've made to your code alongside the code itself. Note that this is broader than just Git and GitHub. You can do this with storing different versions of things on Dropbox or Google Drive or something like that, or just creating multiple versions of a file that's like version 1, version 2, version 1 underscore final, version 1 underscore final, final, final. That's also source control. A repository is, where is it? Which one? The current version of all code and documentation for a project plus its history. So source control is this practice of storing the code along with its history. Commit is a pointer to a version of the main, A commit is the smallest unit of a code's history, a set of changes. And fun fact, these at Google are called CLs, or short for change lists, which I feel like is actually more intuitive than commit. So a branch is a pointer to a version of the main code that diverges from the main line of development. And clone is to create a copy of a repository that you can edit on your computer. All right, so that was fun. When I upload this later, I'll match all of these so you can have the answers. All right, so just to remind you too, there is this vocab list that we keep track of, which I suppose if you really wanted to, you could have opened it up and cheated and not actually learned anything from this. Okay, so why do we need Git flow? Remember, Git flow is this practice of how to create multiple branches so that you can work on things in parallel. So the main reason is that when you're working on big projects, a lot of people are committing code at once. So source control allows people to edit the same code at the same time using different branches. So critically, doing source control and following Git flow isn't going to just like resolve all your merge conflicts for you. You're still going to need to like figure out like, okay, which piece of code is the correct piece of code. You're going to need to like check Git is going to make mistakes, things like this. Git flow is this way of managing that process so there's as little of that as possible, basically. Okay, so what are the advantages of Git flow before I actually show you how it works? It allows for multi-user development and testing. It protects the main code so that you never end up with a situation, or you rarely end up with a situation where your main code that your users are actually using is broken. It makes it easy to go back to a stable point if something breaks. So it's got like series of checkpoints along the way. And it's intuitive that you can perform work in parallel on one or more feature branches. Okay, so let's take a look at how Git flow actually works. So remember, today we're just going to do the conceptual overview, and then tomorrow I'm going to give you a demo of like how I would actually go about setting up Git flow in a real repository, and then you'll get some practice doing it yourself. So we've got the main branch, which whenever you make a new GitHub repository, there will be one branch that is usually called main. So the first step in Git flow is to set up a develop branch. So you create a branch based off of the main branch. You then create feature branches off of the develop branch. And this is where you're going to actually do all of your development. So if you want to add something new, you create this feature branch off of the main branch, off of the develop branch. And you might do this several times. So basically, every time you create a new feature branch, you're going to create it off of develop, except when you're like creating like a chain of commits or of pull requests that are basically building on a particular feature branch. So you could like continue this process down and have like things that continue to develop off of this feature branch. You can make several commits, you can go along your merry way, and then you're gonna pull request your feature branch into the develop branch. And then once you've made enough, once you've added enough features onto develop, you pull develop into main. So the critical nice thing about this is that before you merge develop into main, you can like check that develop is working properly. So if you have several different feature branches that you want to all merge in the same time and see how they all play together, develop is the branch where all that like integration happens. And then main only gets affected once you're happy with the develop branch. And then you just continue. You'll keep the develop branch going, you'll keep the main branch going. So they sort of continue in parallel. So now that I've given you this overview, we can look back at the advantages of GitFlow. Allows for multi-user development and testing in the form of multiple feature branches that are all built off of the develop branch. Protects the main code by having develop be the place where all the actual integration of different features is happening rather than main being the place where that's happening. Easy to go back to a stable point if something breaks. You have your, even if after all of that you end up breaking main, you can always go back to the previous version of main, go back to a previous version of develop. And then, you can perform your work in parallel on one or more feature branches. The last thing I want to say about this is a confession that I don't always follow GitFlow. Scandalous. And the reason I don't follow it is because sometimes it's a lot of work that's unnecessary. I'm going to give you examples of times when I do and times when I don't follow GitFlow. So I tend not to make a develop branch unless I expect a lot of changes to happen at once. So in the main code that I manage that has a lot of multi-user development is called Orbitize, and you guys are going to interface with Orbitize a lot over this week. So I have made a develop branch in the past in Orbitize when I expect there to be a lot of users like making changes at once. So for this particular code, it happens to be, it's usually just before releasing new major versions. So when I know that there are going to be a lot of new features happening, we're all going to be merging them together, I'll make a develop branch and work out all the kinks and then merge it into main. But if there's just like one person working sort of over the course of a couple weeks or months, or a couple of people, and I'm not expecting lots of conflicts, I won't necessarily have a develop branch. I also used a develop branch when I was working on industry code, and in particular, when code is going to be pushed to I want to say real users. Orbitize users are real users, but when people are going to be running your code on their phone or something, and it's going to affect a lot of people. It's pretty standard in industry to have a protected develop branch so that you're not releasing things to users until everything's worked out. And also keep in mind that each developer is going to follow their own flavor of GitFlow. So in particular, you might not always see a branch called main or a branch called develop. So for example, when we were working on version 3 of Orbitize, our develop branch was called v3. It wasn't called develop. So it's good to check in with the local standards of how you're going to follow GitFlow. All right, so that's the overview. Tomorrow I'm going to start with the demo, and then we'll let you all actually implement GitFlow yourself. So I just want to very quickly go through the closing slides for today. Can you see the screen?
Yes.
Okay, great. All right, well, you survived day 1 of Code Astro. Give yourselves a round of a hand. Yay. All right, so I want to remind you of how to ask questions. A, often. B, you can ask in the chat box on Zoom. C, you can ask on Piazza. And D is the 4th letter. D, you can ask on Discord. So I'm going to give you 5 minutes. Please ask a question on Piazza right now. It can be about anything you were unclear about from the lessons today. The main point is just to get you, like, make sure you understand how to use Piazza and break the ice so that you all start asking questions on Piazza. All right, go for it. All right, great job, everybody. Thank you for asking all your questions. I really like this. I like Piazza too because you as the participants can then scroll through and like see if there are questions that are relevant to you. So yeah, I hope it's useful. All right, so I just want to remind you of the goals for today. The lesson goals were to identify which development environment is most appropriate for the programming task. So Jason talked about VS Code versus Jupyter Notebooks, etc. Second, to decide when and how to design software using functional and object-oriented paradigms. Use Git to contribute version-controlled code. We're going to go over Git more tomorrow, so don't worry, you're going to have plenty more instruction in Git, but you should at least start trying to practice with it and using it today. And then also defining Git flow and giving examples of the advantage of Git flow. The project goal for today, to remind you, is to decide on the purpose of the package and write a central function or class. A tip from past Code Astro participants is to check pypy.org to see if your package's name already exists when you're deciding on a name, because that'll save you some trouble down the road. So we've got 3 optional lessons today. This is the day with the most optional lessons. We've got one on NumPy Pandas starting at 2 p.m. At the same Zoom link and for in-person people in room 430. Then about Matplotlib, and then about AstroPy. And just to give you a little bit of an idea, these are not necessarily like, here's how to use NumPy from scratch, here's how to use Matplotlib from scratch, but more about sort of the philosophies of these packages and how you use them in best practices in open source programming. Also, no more apologizing. People apologize to me all the time throughout this workshop, and that's very silly. This workshop is for you. If you can't participate in some expected way for any reason, that's okay. You should use the resources and materials however is best for you. And me and the other TAs and instructors, we're not evaluating you. We want to help you learn. So please take that to heart and don't feel like you need to say sorry. Also, don't sell yourself short. I know it gets to be a lot during this week. There's a lot of information that we're fire hosing at you, but you can do this and you all belong here. Yeah. Yep.